What we have to do now is that we have to find the solution to this game. How are we going to do this? Step number 1 is that the patient, or player 2, in our case, forms beliefs mu and gamma, right? And gamma. For the sake of simplicity, I have assumed that x is equal to 1. Step 1. The patient, player 2, forms beliefs. And those beliefs were what we have looked at already, mu and gamma. Now we have to solve for the expected utility of player 2 and look for the intersection of best replies. The expected utility of player 2 for not testing, given he receives the message recommend from the doctor, is equal to 0 times 1 minus mu plus 0, 0 times mu. And the expected utility for player 2 for choosing test, given he receives the signal recommend, or the message recommend from the doctor, is going to be 1 minus mu 1 minus x plus x times mu. In order to find the threshold of indifference, where player 2 is indifferent between choosing not to test or to test, given he receives a signal and he doesn't know whether he's here or here, we equate the expected utility of player 2 for not testing, given he receives the signal to recommend the test, equal to the expected utility of testing, given he receives the signal recommend. Since all of these are zeros, we know that's 0, and what we solve for in the end is going to be 2 mu minus 1 is equal to 0. And the reason why I'm saying 2 mu minus 1 is because I've replaced my x's with 1. If we solve for mu, mu is then equal to half. If we do the same process for gamma, let's put this here, we're going to find the indifference threshold for gamma. So we find the expected utility of player 2, given that he receives the message not recommend the test. If he chooses not to take the test, player 2 gets 0, 1 minus gamma part of the time, and he gets 0 gamma part of the time. His expected utility for choosing test, given he receives the signal not recommend, or message not recommend, is therefore going to be minus 1. Okay, remember that our x's have turned into 1s, times 1 minus gamma plus 1 times gamma. As you can expect, payoffs are symmetric, and therefore gamma is going to be equal to half. Now what do we do with this? After we've discovered our threshold of indifference for player 2, right, for player 2, we have to check for best replies. And you know that this requires us to go through our box, right? We set up a little matrix where we set up our indifferences, right? The equals, the greater than, the less than, greater than, less than, equal, less. However, before we do this, I want to give you a very simple example before we move on to analyzing all the possible cases. So let's say mu and gamma are the same as p. Why? Because beliefs are automatically consistent, because the signals aren't costly and there cannot be any updating. So let's take an example. If P, let's say, is a third, and as we've already said, and signals are costless, the patient's beliefs coincide with priors, which means that mu is going to be equal to a third, just as P. So all we really have to check is whether the expected utility of player 2, for let's say choosing to test, given he receives the signal R, is greater than or equal to or less than the expected utility of player 2 from choosing not to test, given he receives the signal R. Now that we have P, we can just simply plug it into our previous equation, right? Our expression, which is going to be just a third times 1 plus 2/3, which is 1 minus mu, equaling 1 minus P, times minus 1. And we're going to still check whether it's greater than or equal to 0, right? Plus 2/3 times 0. What we find is that, in fact, negative third on the left-hand side of the expression is less than 0. Correct? Which means that there is an incentive which the player or the patient not to test, because he has a higher payoff when he doesn't test. This is one of the most important points about cheap talk, okay, where priors are the same as posterior probabilities. I would like to check for pooling equilibria first, since they are easiest. Let's say we have a recommendation regardless of the benefits of the test, which simply means, in my little drawing, we're on the right-hand side of our branches, okay? And where gamma is a free parameter. Okay. So for this we have b plus 1, 1, 0, 0, b minus 1, minus 1, 0, 0. The doctor's message is not informative. That's obvious, right? These are the beliefs that the patient holds. Since mu equals half and gamma is a free parameter. Why? When mu equals half, the patient is indifferent between testing and not testing for any p less than or equal to half. We just saw the example where if we inserted a third into our expected utility indifference for player 2, which is less than half, the incentive was not to test. In other words, the expected utility, just to put this in terms that we've seen before, for not testing is greater than or equal to the expected utility for testing. And we found that that was true in the case for our threshold mu of this expression. So the patient chooses not to test, which means the doctor's recommendation is not followed. You say, well, what about the other pooling equilibria? What if we consider the case where mu is the free parameter and the same holds true? Since our payoffs were symmetric, we can then generalize this scenario, which is the opposing scenario for the other pooling equilibria, that the expected utility for player 2 for not testing, given he receives the signal not recommend, is greater than or equal to the expected utility for taking the choice test given he receives the signal not recommend. And that was shown that 0 is greater than or equal to 2 gamma minus 1, where this expression is negative for all p less than half. Our conclusion, therefore, becomes that for all mu equal to gamma that are less than or equal to half, the patient does not follow the doctor's message. These equilibria, in which the recommendation of the doctor, player 1's signal, is ignored, is called a babbling equilibria. These are babbling equilibria. Why? Because it's as if whatever the doctor says is just inane babble. The doctor is babbling nonsense. This is not always the case, but I'm just showing you an environment in which it can be possible. What this means formally is that every cheap dog game has at least one babbling or pooling equilibrium. Okay, so babbling is simply another word for pooling. So without loss of generality, if the receiver believes that the sender's message is independent of the sender's type, then the receiver will use his prior beliefs to choose his actions. This is what we saw in the example of p less than a third above, and we've generalized now for any p less than half. If the receiver ignores the sender's message, the sender is indifferent to the message, and it does not influence the receiver's action. All messages have the same cost, which is 0. This holds whether all types of senders send different messages, a combination, or the same message.